For those who are new, this series uses www.falstad.com for circuit simulations. Welcome to the LRC circuit episode of the Falstad simulation series. They are very important in electronics because they allow us to control frequency, filter signals, and store/release energy efficiently. As you can see, the circuit is divided into two parts. First, we will examine the situation when the switch is opened. As the name suggests, this circuit is a combination of three components: L for inductor, R for resistor, and C for capacitor. If you don't know much about them, or if you need a quick refresher, feel free to check out the previous videos. Briefly, the capacitor, C, stores electrical energy in the form of voltage. The inductor, L, stores energy in the form of magnetic field and controls how fast the current changes. The resistor, R, limits the current and causes energy to be lost as heat. When energy moves back and forth between the capacitor and the inductor, the voltage and current in the circuit can oscillate like a wave. The resistor affects this oscillation by slowing it down over time. When we look at the resistor graph, we can see that the voltage and current are in phase. Why does the voltage and the current phases are different for inductor and capacitor? So, at the start of the circuit, the charged capacitor pushes current into the circuit. The current tries to increase suddenly, but the inductor resists any rapid change in current. To oppose this change, it produces a voltage across itself. This makes the inductor's voltage appear first, while the current increases more slowly because building its magnetic field takes time. For the capacitor, the behavior is reversed. It can release current immediately, but its voltage cannot change instantly because it depends on the amount of stored charge. So the current flows first, and the capacitor's voltage changes gradually as the charge moves. Briefly, in an inductor, the voltage leads the current by 90 degrees. In a capacitor, the current leads the voltage by 90 degrees. Does the oscillation continue forever? This process does not continue forever. As we can clearly see from the graph, the oscillations gradually decrease over time. This happens because there is a resistor in the circuit. The resistor dissipates the energy stored in the inductor and capacitor as heat, causing the oscillations to slowly die out. So with every cycle, less energy remains in the LC tank, and eventually the voltage and current settle to zero. If we remove the resistor from the circuit, will the oscillation continue forever? In simulation, yes, the oscillation appears to continue forever because the LC circuit is considered ideal and there are no losses. But in real life, the answer is no. Even if you don't include a resistor, the wires that connect the inductor and capacitor still have a small resistance. Also, the inductor has internal winding resistance, and the capacitor has leakage. So in reality, there's no such thing as a perfect infinite oscillation. Now we will examine the situation when the switch is closed. Once the switch is closed, if we look at the current direction, we can see that the current flows in two different paths. But why does this happen? Because the capacitor in the circuit is considered to be in a charged state, and when the switch is closed, it starts to discharge. After a short time, the current flow stops. This brings up a question: why doesn't the capacitor start charging again? So at the beginning, the capacitor's voltage is higher than the supply voltage. Since current always flows from higher voltage to lower voltage, the current starts moving from the capacitor into the circuit. At the same time, the inductor begins to charge. As the inductor charges, its opposition to the change of current decreases, and therefore the voltage across it also drops. When the charging process is almost complete, the inductor's voltage becomes nearly zero. Because the capacitor is connected in parallel with the inductor, its voltage also drops to 0, and at this point, it can no longer charge again. That's all. And if you found this video helpful, don't forget to like and subscribe. See you next time.